Alright, let's begin. So we started derivatives last time, definition. We're going to talk more about that. I guess I probably want to talk about the test first a little bit, though. Didn't want to spend a lot of time on that because I really want to finish 2.4 and maybe start 3.1. But I spoke to a bunch of people, and there are some patterns that I've noticed that are concerning. So at this point, I spoke to maybe 12 of you or something like that. Of the people I spoke to, maybe 4 of you knew that there was a review for the first test online. And 2 of the people who did know didn't do the review. And so that's the first thing that was kind of strange to me. So right now, there are reviews for all the tests online. They're already there. There's a review for test 2, test 3, test 4. There's a review for all the tests, right? So you do have a focus on what you should be studying. And I noticed a lot of you studied using your homework or using the notes from class and using the textbook and really trying to cram everything in your heads. It's not a very efficient thing to do. So I guess I'll just say a few words about that, about how you should be proceeding and what you should be learning from the first test. I did a long talk about this before, about how to study for a different class. It's also on video at some point. Maybe I'll send you guys a link, but I guess I'll give the highlights now because I really don't want to spend a lot of time talking about that. So one thing, the review is where you start. Okay, so anyway, let's talk about that first. How to study. Step 1. Do the review. Do all the review problems. Don't do some of the review problems. Don't kind of look at the review problems. Don't kind of scan the. Do the review problems. That is where you start. That is the first thing, right? Step 2. By the way, what you should kind of do, I asked a bunch of you if timing was an issue. A lot of you said no, maybe half of you said no. But you still want to practice under timed conditions. Right? Put a little pressure on yourselves. A lot of you studied from the homework or the notes. Not a very efficient thing to do. It's not something you should be doing at all, really. That's kind of a last resort. What you want to do is you go through all the review problems. Do it under timed conditions, right? So you put yourself under pressure, right? Now after you go through all those and you check your answers somehow, if you don't know how to check them yourself, go to the tutoring center or something and try to talk to someone about what the correct answers would be. And then you'll start to see patterns. You'll start to figure out, oh, I have a problem with these kinds of problems, or I have trouble doing this kind of manipulation, right? So you'll go through the review problems and you'll notice that, right? So then you kind of know what to focus on, and those are the kinds of things that are going to come up on the test and can kind of trip you up. And only then you would go back to your notes or the homework and realize that I need to look at these particular problems. I'm not going to go through 100 problems on the algebra review. I only need to look at 5 problems on the algebra review because those are the things I have trouble with, right? You have to remember, you have a finite amount of time. A lot of you I spoke to work full-time or close to full-time. A lot of you are doing 5 classes, 4 classes, and you have to devote a lot of time. You have to be efficient. And I know a lot of you are lower freshmen. Most of you that I spoke to so far are lower freshmen. So it's a different kind of culture. College is different from high school. You probably start to realize that now. It's a different thing. It's a different sense of things. It's no one's holding your hand and no one's expecting you to just, oh yeah, I'll just study my homework. No. Efficiency. Get the job done. There is a goal here, right? There's always something you need to accomplish. You have a finite amount of time to do it. Organize yourself. Learn how to organize your time. Work on what you have to work on. It's not just about working hard, it's about working smart. You don't want to be the person spending 5 hours a day studying and still getting bad grades. It can happen. You do not want it to be you. Focus. Have priorities. The review problems are the priorities. I'm telling you what I'm going to be testing you on, right? You don't want to study everything, right? you're studying the wrong way, you're preparing for the wrong thing. As I mentioned to some of you, it's kind of like I'm telling you, oh, we're going to have a sprint and you're studying for a marathon. Sure, you're getting some exercise in, but it's not the right kind of training, right? You're training for a long distance thing when it's a short distance thing, and you need to have a burst of speed and you're training for the long haul and dripping a little bit. You're not going to have a good result. The review problems tells you what you need to know. You're going to go through those first under time conditions. Because again, if you don't time yourself, it's like, oh, I'm doing the review problems while watching Netflix or, you know, while on Facebook. You're never really going to know if you have a problem because you have all the time in the world to think about it, right? And then you can come back and you have that. I'm sure a lot of you have noticed this. Sometimes you're in a test and you blank out. The moment you walk out the door, everything comes back, right? I'm sure you guys have noticed that. That's what's going to happen if you're on Facebook while practicing, right? Because your brain has this long time to think about the problem. Even when you're watching Facebook, your subconscious mind is working on the problem, and you might think you're going through it and everything's fine. But the truth is, if you gave yourself a 5-minute time limit, you wouldn't have figured it out, which in a test is what's going to happen, right? So you practice, you need to train for what you're going to be doing, right? You don't have forever in a test. Do not study as if you have forever, right? So you study the review problems under time conditions. That is going to be the first thing. Step 2. Go over what you have trouble with. From step 1. And again, remember, efficiency is what we care about. So the first place you would do this is the quizzes, right? Not the homework. So even at step 2, you still wouldn't go back to the homework, right? Why would you go to the quizzes? Well, remember, there's the whole idea of you need to train for what you're going to be facing. What you're going to be facing is problems written by me, not the textbook, not web work, right? You need to train for my problems, not anyone's problems. What are my problems? The ones I give you on the quizzes, right? That's going to give you the level of difficulty or give you an idea of what you're going to be facing, right? So you're going to go to the quizzes, and you're only going to go from what you had trouble with from here. You don't have time to do everything. You have other classes, you have work, you have a lot of things going on in your life. Study efficient, right? So after this, you go through the review problems, time yourself, put yourself under pressure. That's where your mistakes are going to leak out. That's when you're going to realize what you do or don't understand, and you need to understand quickly, right? After that, you go over what you know and have trouble with. Maybe you can go to the quizzes, maybe you can go over the review again with a tutor or something, and you study for those. And step 3, perhaps do similar problems from the homework. Step 4. Okay, so once you go over everything and you think you filled in your gaps by doing step 2, probably ignoring step 3, because again, you want to be efficient and you want to study for things that you will be facing. You go and you make your own tests, right? So you look at the review problems and you just pick out a different type of each problem, right? So you go through this list of problems that I gave you for the review, Pick out one of the problems that deals with an LI. Pick out one of the problems that deals with an ETX. Pick out one of the problems that deals with difference quotient. Pick out one of the problems that deals with this, right? Have a good variety. Do that under time conditions, right? So you're going to make your own test and you're going to do that under time conditions. And you'll find that a lot of the gaps that you missed here, you filled in a lot of them, but you might have one or two that sneak out. And then you reevaluate, right? And then you go back here and you know, okay, that's another thing that I need to start work some more on, right? 5 steps. It seems like a lot, but it's a lot more efficient than going over your notes and homework. And you will have a better result at the end of the day. I know a lot of you are bio majors, you want to go to med school, or you're trying to, you're doing science degrees, you want to get into research. You need to be efficient and you need to know how to prepare for things. And you need to be aware, right? So it should not be a surprise that there were review problems, because I did tell you guys about it several times in class. It's recorded on video. It should be in your notes. It's not something you should miss. And even if you missed it, it shouldn't be something you should skip in your preparation, right? If I told you, these are the problems I wanted to practice for test 1, why would you ignore them? That doesn't make any sense, right? So you need to be efficient. You need to train for what you will be facing. And what you need to remember for Calc 1, and a lot of the classes that you will be taking on this track, in this math track, a lot of you have to do the next one, 209, it's standardized. It's standardized problems. There are no curveballs, right? Everything I'm asking you has been asked before, right? If you look at all the old tests and all the same kind of problems come over and over and over. There should be no surprises. There should be no, oh, I've never seen this before. It's not going to happen. If you prepare correctly, you will not be surprised. You will know exactly what you need to know and how good you need to know it, right? It shouldn't be the case, or what review, right? So I'm telling you, a lot of you guys don't know this, but, and a lot of the other people who have been in college for a while, they can tell you, a lot of professors aren't going to do even this much. There are a lot of professors you're going to see in college, they're not going to give you a review. What do I need to study for the test? Everything, right? You have this information available. Take advantage of it, right? They can tell you, all the people who are like sophomores, juniors, seniors in here, let them tell you. No one's going to tell you review problems to do for stuff. You're going to need to know, you're going to need to evaluate on your own what's important. I am telling you what is important. Do not let that information go to waste. Do not study in vain, right? Don't study for 5 hours when you can study for 1 hour. It doesn't make any sense, right? Use your time efficiently. Use your time well. Be able to track your progress. And you want to do efficient work. Do the least amount of work as possible that has the most amount of impact, right? I know a lot of you are studying also economics and psychology and things like that. You guys heard of Pareto's efficiency? Is that something you guys have heard of? No? Okay. Well, that's something that shows up all over the place. Basically, it says that 80% of your results come from 20% of your work. Right? You need to maximize that 20%. Right? You'll be surprised. A lot of you are studying all this stuff and you're thinking, oh, calculus is so hard. It's like this mountain of work that I have to get through. No. Like everything I tell you in the class, if you know 20% of it very well, you already have a B. You need to know what to focus on, right? Study efficiently, and don't go through life blind, unaware. Like if you have a resource, it shouldn't be the case that you don't know about it. Like that should not be something that happens, right? So, yeah, and again, as I said, I gave a long talk about how to study for a standardized test before to my other class. Probably I'll send you guys a link to the video. I did it for a more advanced math class, but again, the concept is kind of the same. And yeah, so, and a lot of people, and this is again, most of the people I spoke to, sure, they didn't do that well on the test, but overall I can see that they're not completely clueless. I know that if they had studied correctly, they would have done very well. I get that impression. No one has talked to me where I'm like, you really needed to talk to me. So I know you might be shy, but you need to come and talk to me if you didn't do well, so we can actually know what the problem is. So a lot of you, I'm very confident you can do well on the next test if you follow these steps, because a lot of people just, they didn't do the review prompts, or they didn't even know about it. right? That should not be the case, right? You do not have a lot of time. You need to get things done.
What is the
so yeah, I don't put times on the exam because I want to be able to speed up or slow down. But if you follow the syllabus, if you look in the syllabus, do I have a copy here? Yeah. So in the syllabus, you'll see that our next test is after section 3.5. So it'll be about a week after I cover that. An estimate maybe. So I'll definitely finish 2.4 today. 3.1 and 3.2 probably finish next class. 1, 2, 3, 4. Maybe 6 classes from now, roughly. But you'll know it's coming up because you'll see where I am in this list, right? It's once I get through those topics, the exam is after that. And for the first 2 tests, you'll have at least a week of prep work ready. As it's getting later in the semester, you're not going to have that. So for example, the last exam is on the last day of class, right? So you're not going to have a lot of time for that. So you really need to get ahead. And that's what I'm saying. Like here, like this is a resource. The list of topics that I gave you guys, you know what's coming. You have prep problems there. You have review problems there, right? You shouldn't be going into something blind when there's no need for you to go into it blind, right? You know what's coming. You should prepare for it. So again, that's just some general advice, but again, I need to give you guys specific advice for your specific situation. So if you haven't spoken to me yet, you need to talk to me. And some of you, I told you guys what to do, and you'll check in with me later. But to begin with, that's kind of how you're going to want to approach things from now on. Not only in this math class, but in every math class. As much as possible, try to narrow things down into what you need to do, right? And it turns out in a math class, that's actually a lot easier than in almost any other class. A lot of people think of the math class as the hardest one. It's actually the easiest one to prep for if you really know what you're doing and you're really efficient. Okay, so I spent a lot of time talking about that. We'll probably talk more about that later on. But yeah, doing things like that is how I got through college, even in non-math classes, right? I kind of narrowed things down. Probably I'll talk about that some other time, but right now I really want to get through chapter 2, maybe start chapter 3. So we're going to move on. But yeah, if you haven't spoken to me yet, come talk to me so I can see. As I mentioned, there are a lot of people who really need to talk to me, and I haven't met any of those people yet. Don't be shy, come talk to me, because we need to know what's going on. Hopefully the second test will be before the drop date, so you can really have, and by that time you really want to get ahead of things. So let's actually move on. We're going to continue with section 2.3. Let's recall some important facts. And again, there are a lot of things from the notes that homework and notes, it kind of, when you're approaching something, you really want to approach it from a wide-angled lens, right? So the homework and the notes will give you this comprehensive overall understanding. But when it comes to doing well on a test, you want specific targeted knowledge, right? It's a different thing, right? So even a lot of the notes, you read through all your notes, again, studying for a test, it's a waste of time, right? You should know what to pick out from the notes. For example, if I ever start a class with recall, it means that that piece of information is important, right? Or if I draw something in a box and I put asterisks around it, that piece of information is important. If that only happens once in a lecture, you can essentially ignore everything else in that lecture. Just make sure you know that thing and how to apply it, right? Be efficient. Okay. So recall last time we defined the derivative f prime of x. The derivative. What was the definition? Limit as h approaches 0. F of x plus h minus f of x all over h. That definition is super important to know. You're guaranteed to be tested on this. Oh, I didn't know you were going to put a problem like that. I'm going to put a problem like that. Okay, so that was the definition of the derivative. Now what that actually gave us was what? Like, how did we think of the derivative? Right, when you hear that word or you see this formula, what do you think? Slope. That should jump out to you. In particular, what slope? Slope of the tangent line. Right, in particular, a formula for the slope of the tangent line. At a given point. What's another way we want to think about derivative? What's another way? Rate of change. Right, so that's a lot of math talk. Slope. You don't see slopes in the real world. Rate of change, how fast something is changing. Right? Instantaneous rate of change, in fact, is what the derivative is. We know about average rate of change, which is just the difference quotient without the limit on it. Throw a limit on it, now it's an instantaneous rate of change. Or how fast something is moving. Right, so this are some concepts that you really want to just have in your head. Because then you'll know when you need to take a derivative based on what you're being asked to do. Okay, so you need to know this definition. You're definitely going to be tested on it. You need to know what the derivative means. So, you know, for example, one way you think of derivative is the slope of the tangent line. So, you know, if I'm ever asked you to find the slope of a to find the equation of a tangent line, oh, where do you get the slope from? The derivative, which is this formula. And that helps you find the slope. And once you find the point, which I assume you would know how to do now since algebra and pre-calc, you would be able to find the equation of that line. Right? Just by knowing what it means gives you an advantage. Just being aware. Another thing we want to do, so yes, what's a tangent line? And we're going to have uses for this tangent line. It's not just a party trick. Tangent line is actually useful, and I'm going to show you some uses of it later. But yeah, basically it's a straight line, y equals mx plus b. What makes it a tangent line is where the m comes from. This is when the m, this is from f prime of x evaluated at a certain point. Right? That's what makes a straight line a tangent line. Right? So if I ask about a tangent line to a curve, it means I want the slope to come from the derivative of that curve at some point. Okay? But a tangent line is just a straight line. So everything you know about straight lines applies to tangent lines. It's just the slope comes from a particular place. Right? So these were the main ideas from the last lecture. And we did a lot of examples of just computing this for different functions. And we're going to make that a little bit easier as we move along to chapter 3. But for now, that's what I wanted you to remember from last lecture. And so these are things you should do. And was there a question? Okay, so that's just remembering. Right now, I just want to talk about, we'll come back to this later in the semester, but I just want to mention them now, some applications of derivatives. Why would we even care about any of this at all? Applications of derivatives. Well, one application is physics, which a lot of you have to do some sort of physics. For example, motion, right? Which I kind of illustrated before. So for example, if you know that S is for some reason the standard letter used for position. But if you know you're given a position function of some object, then it turns out if you take the derivative S prime, you end up with the function v of t, which is the velocity. Right? Turns out velocity is the rate of change of position. Right? Now if you take another derivative, mention second derivative today, s double prime. That gives you the function a of t, which is acceleration. That is the rate of change of your velocity with respect to time. Now we're going to go through this. I don't know how many of you have actually done physics before. But if you're in this class and you have to do physics, odds are it's the Physics 203, which is non-calculus based. But it turns out that all those formulas they give you in that class, they were derived from calculus. So if you actually understand this better, you'll be able to understand that better. And you'll have less to memorize, because you know how to derive all the formulas, right? So yeah, physics of motion, calculus actually applies. A derivative gives you a rate of change, how fast something's moving. So if you tell me how something's moving, and I want to figure out how fast, take a derivative, right? How fast is the speed moving? Take a derivative, right? Every time I want to know how fast something's moving, I'm going to take a derivative, right? So derivatives will apply to things like motion, or how something is moving. And not even just in the physical sense. It's if you're tracking inventory, or you're tracking the growth of a tumor in a patient, or you're tracking anything where you know its current size and you want to figure out how fast is it growing, you're going to take a derivative. Right, so that's one application. Another application is economics. So for those of you who are economics majors, things like marginal analysis is one place you're going to use derivatives. But we're actually going to talk about this after we do optimization, or even before optimization. Marginal analysis. So something like, if your C of x is, for example, a cost function, to produce X items, products or services or whatever, then it turns out if you take the derivative of C of x, that gives you what's called the marginal cost function. And this would apply to other functions in economics that you care about. So if you have a function for revenue, then you take the derivative, you get what's called the marginal revenue. Or if you have a function for profit, you take a derivative, you get what's called the marginal profit. Now what that actually tells you about is cost to produce one more item. So basically that talks about what's happening on the margins. That's why it's called it's called marginal, right? So if you have a function that tells you the cost to produce 100 items, right? So you know, to produce 100 products, it costs this much. How much would it cost me to produce 101? C prime of 100 is going to tell you, right? And so you can actually predict in the future what something's going to cost if you keep moving, right? And then once you figure that out, then you're figuring out, well, that's going to eat into profits. You can kind of analyze things, right? So calculus is used to predict in the future how things will change if you push the margins. What if we did a little bit more, right? What if we did produce 101 million items instead of 100 million items, right? How is that going to affect our margins, right? So that's our process of economics, and we'll actually go through it. That's an application. Things like population dynamics. Right? So if you're studying populations, ecosystems, you're doing biology or anything like that, you need this stuff, figuring out how fast populations are growing. Or what their size will be at some point in the future. Right, so there are a lot of things that go into this. It's not as simple as you might think. So for example, if you're the US government and you know that right now I have 300 million citizens to take care of, how many citizens will I need to take care of in 10 years from now? What resources will we need? Calculus is where you're going to go. That's where you're going to analyze. With some statistics and probability, of course. But it's all about predictions and kind of seeing what things are going, how fast they're moving. You know, 10 years from now, where do we expect to be? this is one of those applications. You can also study things like exponential growth and decay, which is another topic we're actually going to do in detail later. Right? So some items under here that will exhibit exponential growth, for example. For example, a population. Populations do not grow linearly, they grow exponentially, right? Your population doesn't always add the same amount of people. The more people you have, the more babies they make, right? So it turns out that they increase at an increasing rate, right? A population graph that's growing will look like that. Because the more people you have, the faster your population is growing, right? So population will fall under here. Things like finances, financial markets, right? If you're having compound interest, money grows like this. It doesn't grow in a straight line. Right? As well as if you have like debts that you're paying in certain interest on, you should be aware that it's going to grow like this. So when you're planning for the future, you're not thinking of it growing like this, which can be a big miscalculation. Right? So if you're in finances and tracking financial markets, your calculus is going to be very important. Things like decay, radioactive decay, right? So anything that's radioactive and is decaying at a certain rate, and you want to figure out that stuff, you will go to calculus. You will use derivatives. So if someone wants to figure out, you know, when is Chernobyl going to be habitable again, calculus is what they're going to use to figure it out. So there are a lot of applications that apply to a lot of things, that a lot more than I'm saying here. But these are just some things that we're going to be touching on later in the course, so you should be aware that these are all applications of derivatives, and we're going to actually be studying them. Moving on now, we're going to go further into derivatives. These are just some things to keep in the back of your mind while we're doing this. And you can start to think about how it would apply, so that when we start to cover them, you won't be behind. Any questions so far? Just throwing information at you right now. Let's get some more technical things. So this is kind of section 2.4. I'm kind of doing them both at once. So let's talk about that. So we know f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h if it exists. Now remember, it's a limit, so it's possible for it not to exist. So right now what I want to talk about is the case where it doesn't exist. When would a derivative not exist? When would I not be able to do calculus to solve a problem? Or when do I have to be careful when I'm doing calculus and I have to think of things a little bit differently? When does the derivative not exist? One case, which should be obvious, when the function is not continuous. So for example, if I'm looking at y equals 1 over x, and the graph looks like that, and I ask you, what's the derivative at x equals 0? There is no derivative at x equals 0. The function doesn't exist there. It's not continuous at x equals 0. Right? What am I going to draw a tangent line on? There's nothing to draw a tangent line. So obviously if your function doesn't exist somewhere, you can't take a derivative there. Similarly, if I ask you about y equals ln x, which you know looks like that, or you should know by now it looks like that, I can't ask you, what's the derivative at x equals minus 1? There is no function at x equals minus 1. I can't draw a tangent line here, right? So obviously in the cases where the function isn't around, you can't find a derivative because you can't draw a tangent line. And the derivative gives us the slope of the tangent line. What's probably not so obvious is that a function can be continuous and can exist, and you still can't take a derivative. Consider this function. Absolute value of x. And I ask you, what is the derivative when x equals 0? Let's try to answer that question. So if I call this f of x, I want to find the derivative when x is 0, right? So what's that going to be? Limit as h approaches 0 of, what would I have here? It's x plus h, but I know my x is 0, right? So this is going to be f of 0 plus h minus f of 0 all over h. What's this guy? Absolute value of 0 plus h minus absolute value of 0 over h. Okay? And what's that going to be? What do we have now?
H over h.
Do I have h over h? I don't have h over h. What do I have? What does this simplify to? Come on, talk, don't be shy. Zero plus h is? So what do I have left here? Absolute value of h, okay. Absolute value of 0 is 0, so nothing, I don't have to write anything. In the denominator, what do I have? H. So I have absolute value of h over h. Now what is that limit as h goes to 0? It's not going to be 1. What is absolute value of x equal to? Okay, when is it positive x? If x is greater than or equal to 0, the absolute value gives you x. If your x is less than 0, what does it give you? Negative x, right? Which means that this guy actually splits into two parts. This limit as h approaches 0 of this function. It's either going to give me h over h if my h is greater than or equal to 0, or it's going to give me minus h over h if my h is less than 0. Right? Which is, it's either going to give me 1 or minus 1, depending on what side of 0 I'm on. Right? But my limit is approaching 0. So basically what happens is, if I'm approaching from the right, I get 1. If I'm approaching from the left, I get minus 1. The limits don't match up. Right? So basically this guy here is going to be the left-hand limit. This guy here is going to be the right-hand limit. They're not the same. So it turns out that this guy does not exist. Now let's talk about why it does not exist. That's kind of strange. Let's see what actually happened. What does the graph of absolute value of x look like? It's a V. Goes here, boom. Goes here, boom. Now at x equals 0, we have a sharp corner. Now if I ask you, can you draw a tangent line there? What would the tangent line be? Well, actually almost anything. right? This is a tangent line. Touches it at only one point locally, but so does that line. So does that line. So does that line. So does that line. There is no tangent line. There's no well-defined tangent line at that point, right? There are tons of lines that I can draw that only touches one point. Tangent line undefined. Which gives us the second case in which a derivative does not exist. Derivatives do not exist where there are sharp corners. So for the future, if I give you an absolute value function, you need to figure out where does the sharp corner happen, because you can't take a derivative there. Right? You're going to need to know when is my calculus going to work, when is it not going to work. Obviously, if the function is not defined, it's not continuous, you can't do calculus there. And at sharp corners, calculus also breaks down. In pretty much every other case that you will have in this class, things will be fine. But be aware that there are cases where things are not fine, and you have to worry about it.
So why does the absolute value of h of h exist anymore? It doesn't exist anymore.
The limit as h approaches 0, it doesn't exist.
Then why is that again?
Because one side gives you 1 and negative 1. If I were to draw the graph absolute value x over x, the graph would look like, from the right side, it will come to 1, and from the left side, it will be at -1. So the left and right hand limits don't match up. Yeah.
Does it apply for every absolute value function?
Yeah, everyone that has a sharp corner, yes. Obviously, if what's inside the absolute value is always positive, then it won't matter. Right? So if I ask you about x squared plus 1 and put that in absolute value, it's not going to matter. You get exactly the same graph, and I can find derivatives anywhere. Right? But once what's inside absolute values can actually switch signs, you're going to get a sharp corner somewhere. So you have to be aware that things can break down. Okay, let's move on. So here I talk about differentiability implies it's continuous, but continuous doesn't mean it implies it's differentiable. I don't think you need to summarize that. Just know derivatives don't exist if the function doesn't exist or there are sharp corners. That's basically what you want to take away from those splurge there. Now let's talk about something else, something that has a lot of meaning to us, as the derivative would be. Talk about the second derivative. So you saw in the physics part, the second derivative had meaning. It meant acceleration, right? Second derivative is actually a lot very meaningful in other contexts as well. This just means take a derivative twice. Right? So take a derivative. Then take the derivative again of the result. So if you do the derivative twice, you get what you call the second derivative. Right? So notation, I already kind of mentioned it when I did the physics example, is 2 primes, right? So f, you write a double prime. That means second derivative. Right? Or you might see in the dy dx notation, this is what it would look like. That also means second derivative. Right? And the notation's kind of generalizing this way. So if I have f triple prime, that just means third derivative. Take the derivative 3 times. Or I can have d cubed y dx cubed, that means third derivative. Or I could have 4 derivatives, or 5 derivatives, or 6 derivatives. And you will keep going. In this class, you're never going to have a reason to go beyond 2 derivatives, but you should know that these guys exist. So eventually what happens is the prime notation, it gets big drawing all these notches. If you want to do 8 derivatives, you have to write 8 notches. They just have, they just put the number in brackets. So they might say something like, if you see a power and it's in brackets or parentheses, right, that means 5th derivative. Right, so if you see a power that's in parentheses, it's a derivative. Right, so you can see something like f to the n of x. That means the nth derivative. Or you see something like d to the n of y over dx to the n. That means the nth derivative. So that's the notation. So in physics, if the original function is the position function, the second derivative gives us velocity. The first derivative gives us velocity. The second derivative gives us acceleration. The third derivative gives us what's called a jerk. So if someone calls you a third derivative, you should take offense. Being such a third derivative, man, you jerk. Fourth, fifth, and sixth, I think it's like they call it snap, crackle, pop or something like that. It gets really funny after a while. But you won't need that. If you're going that high in derivatives, you're in some really deep science research, physicist kind of stuff where you're not going to need to know that stuff. Or you're making a power series, stuff you don't need to know. The second derivative is very important for us though, because second derivative tells us about concavity. How you want to think of this is, remember derivative just means a slope. So a second derivative you think of as the slope of the derivative. Right? The slope of the slope, or how fast is the slope changing, right? Every time you see a derivative, that's how you're thinking. Like that. So when you have a function and you can look at what the slope is doing, but then you can look at what the slope of the slope is doing. And that leads to the idea of which we're going to talk about, concavity. So let's look at an illustration before we kind of talk about what that means. So let's say here I'm plotting 2 functions. So one function is doing this thing. This is at 100. This is at 500. Function is doing this. This is at 100. This is at 500. Let's put meaning on these. So let's say here, this is tracking sales. Right? So I'm a store manager, I'm tracking my sales with a function. X is the time in weeks, months, days, weeks, time in weeks. And this again is sales. So I create a function where my input is the time in weeks, my output is the number of sales I made that week. Right? So I create this function. What you'll notice in this function is that over time, my sales increase from 100 to 500. It also increased from 100 to 500 here. Now, here's the question. Are they the same? Now you can see from the picture that they're the same, but how about this question? Which situation would you rather be in? This one. You can kind of tell, right? Why? What's going on here? Let's look at the slopes, right? So if I draw a slope in the beginning, my line is like that. Now it's like that. Now it's like that. You'll notice that the slopes are leveling off. Really steep, meaning sales are increasing rapidly. But hey, they're still increasing, but they're increasing by less and less and less, right? So it's like 1 week I sold 100 more products than I did last week. But the following week I sold 50 more products than I sold the week before. Right, I'm still selling more products, but overall the increase on the previous week is getting less and less and less. That situation will give you a graph that looks like this. That situation describes the situation where the slope is actually decreasing. Right? So if I look at the slope of the slope, how is the slope changing? The slope is decreasing. The function itself is increasing, but the slope of the function is decreasing. See, right? So you're like inception, you're going deeper, like another level. Right? Whereas here, the slope starts out like that, but then it gets steeper, then it gets steeper, then it gets steeper, right? So this is the situation where overall my sales are increasing, but each week they increase above and beyond what the previous week increased on the previous week, right? So this week I sold 100 more products than last week. The next week I sold 200 more products than I sold the week before, and go on and keeps going, right? So this kind of tells you that, hey, sure, we're okay, sales are increasing, but they're increasing by less. Which means in the future I might predict that, hey, my sales will probably level off at some point, which means I probably need to start doing something. Here you're like, yeah, I'm definitely doing something right, because sales are increasing, but they're going to increase even faster. In the future I can predict that they're really going to take off, whereas this one's going to level off. This one is just taking off, right? Now I can ask about another situation, like this one, right, versus this one. Right? Now if you look at this guy, again, overall you're increasing, but notice here your slope keeps decreasing until it hits a certain point. Now the slope starts increasing, right? This point where the slope behavior changes is called an inflection point, which we're going to describe in detail later on. Right? So here again, this would be called an inflection point. Right? So now let's say you're the same store manager and you're tracking your sales and things look like this or that, right? And the starting and ending point might be giving you the same values, but they actually tell you a very different picture about what's going on. Like what was going on here? Well, business was good overall, they were increasing, but things were looking like they were slowing down. At this point in time though, something happened, and then that started to happen, right? So if I'm a business guy and I want to make as much money as possible, like I want to sell the most products I can, I'm going to want to know what happened at that point in time. What changed here, right? So if I'm looking for how to improve my business, I'm going to look, okay, at this week, what happened that week, right? Did I put up a new ad? Did I start to advertise on Craigslist, or did I start to post flyers around? Did I put up did something happen and there was a stimulus package or something, or here? Things are increasing, and now they're still increasing, but they got worse. Did a recession happen? Was there a natural disaster? You can kind of know where you want to focus your energies, right? Just by looking at the picture. Now, someone who doesn't understand the idea about slopes and concavity, which we're going to talk about, might look at these are the same. Oh, your sales increased from 100 to 500. Someone who knows about calculus can look at it more deeply on another level. Someone who knows that can predict what's going to happen. And that's one of the reasons why the second derivative is important. It gives you another level of understanding of what's going to happen. Prediction is a very important thing. We're going to be using calculus all the time. So now, let's talk about these guys. Let's call this situation, let's call this case 1. I'll call this case 2. I'm going to talk more in detail about these guys. So case 1. A function that exhibits Forget to explain exhibits. This behavior is said to be concave down. Right? So this kind of feature, when you're looking at a graph for how it's bulging, that says you're looking at concavity. Something that's bulging like this, you call it concave down. Notice that. Well, let me just mention this. Right, so it's called concave down. A mnemonic that you can use to remember that is down like a frown. Okay. We're going to talk about that in terms of derivatives, which answers the second bonus problem on your quiz stat from yesterday. What happens here is that the second derivative is negative, right? So you're negative, you're sad, you're feeling down, you're concave down, right? When you shape like a frowny face, you're concave down, right? This means the tangent line is always above the graph. That's just an interesting piece of trivia. You can forget about that if you want. But this you should know. Concave down means it's down like a frown, talking about the shape of the graph. This is how you're going to identify it, when your second derivative gives you a negative value. Case 2, this is called, what's the opposite, concave up. Which you can remember about up like a cup, right? You're down like a frown or up like a cup, something that can hold liquid. This happens when your second derivative gives you a positive value. So you're feeling positive, you're feeling up, you're feeling happy, you smile, you end up with a graph that looks like a smile, concave up like a cup, right? Tangent line always below the curve. Let's call this case 3, case 4. So case 3 and 4, the indicated point is called an inflection point. And what is that? It's a point where you switch concavity. Right? So if you look at case 3, before here you were down like a frown, right? This is concave down on this side, right? At this point though, you switch. Now you're up like a cup. You look like a smiley face. Over here you're concave up. So at this point you switch from concave down to concave up. That point is called an inflection point. This similarly here, you're concave up like a cup on this side. You're concave up. At this point you switch though, you switch to look like a frown. This is called concave down. The point where you switch from concave up to concave down is called an inflection point. Once you switch concavity, it doesn't matter if you switch from down to up or up to down, the point where that switch happens is called an inflection point. An inflection point, as I just mentioned with my example, they're important points. You're going to want to know when that happens, because it means that there was a shift in something. Something either started increasing faster or decreasing faster, or started increasing more, increasing less. So this is called concavity. Note F double prime has nothing to do with increasing or decreasing. It's not a part of the analysis. For example, I can have a function like this, This here is concave down, and it's increasing. I can have something like this. This is also concave down, but it's actually decreasing. Right? What you want to remember is concavity talks about the shape of your graph. It doesn't matter if it's going up or down, I don't care. I'm talking about the shape. How is it bulged while it's going up or down? Right? That's what the second derivative tells you about, the shape. Right? The first derivative is what tells you about increasing or decreasing, if something's going up or it's going down. Right? But concavity does not tell you about that. It tells you about the shape of the graph while you're doing this, which can give you a lot of information. A lot of information. You there? Let's summarize. What do you need to know? Let's kind of summarize these ideas, put them all together. This is how you want to think about things. Let's talk about the function. Let's talk about what does it tell us. Well, how does it tell us? The idea being different derivatives tell us about different things, and we need to know what they're telling us about. So let's look at the original function, f of x. What information do we get from f of x? What does f of x tell us? The y value. What does it tell us? Y values, right? The output, the coordinates, the coordinate you're at, coordinates x comma y, right? If I know the x value, I need to find the y value to find a coordinate or a location. That is what the original function tells us about. It tells us how to plot the y values for each given x values, which makes a picture, how to draw the graph. Tells me where my point should be as a location on the graph. How does it tell us this information? Right, given an x value, plug it in x to find the corresponding y value. At any point, I need to find the location of something, a point that's on my curve. I will look at the original function. That's what it tells me about, right? If I want to figure out increasing and decreasing, I do not look at the original function. It does not give me information about that. If I want to figure out concave up or concave down, I do not look at the original function. It does not give me information on that. The only thing the original function gives me information on is the y values, the outputs, the coordinates on my graph. Now let's talk about the first derivative. What does that tell us? It tells us about slope, so let's actually put it into different language perspectives. This tells us about when something is increasing, decreasing, when something hits a maximum or a minimum. So the first derivative, that's the information you get from the first derivative. So at any point, if for some reason you want to know when am I increasing, when am I decreasing, when am I a maximum, when am I a minimum, right? You will look at the first derivative. You will not look at the first derivative to figure out a location. That's not the information it tells you. The only information you get from the first derivative is these four pieces of information. At no other point will you look at the first derivative for any other piece of information other than these things. How does it actually tell us these things? Well, increasing, that means the first derivative gives you a positive number, right? If your first derivative is positive, it means your function is increasing, because the first derivative is the slope. So if the first derivative is positive, it means the slope is positive. If the slope is positive, it means you're behaving like this. You're going up as you move from left to right. Right? Decreasing just means that the first derivative is negative. F prime is negative. Right? So if I want to figure out where is a function increasing or decreasing without actually drawing its graph, all I need to figure out is where the derivative is negative or positive. Positive first derivative means increasing. Negative first derivative means decreasing. So how would you use this, for example, to figure out a maximum? Well, what is the behavior exhibited by a maximum? It means you look like this, right? There's a point where you're increasing to some value, you hit that value, which is the highest value you hit, and then you start decreasing from that value, right? So what happens in a maximum is this behavior. There is a point here where you're increasing on the left side of it, and you're decreasing on the right side of it, which tells you your first derivative is positive over here, and your first derivative is negative over here. And at this point, the first derivative is 0 or undefined. Right? So what happens is when you switch from positive to negative, it means you switch from increasing to decreasing. So to do that, you'll have to actually either pass through 0, or you can be undefined, which is the case of the absolute value where there was a sharp corner. The derivative wasn't there, but I could figure out it was a minimum. Minimum exhibits the opposite behavior, as you might expect. A minimum happens if on the left you're decreasing, you hit some value, then you start increasing, right? Which means on the left, your first derivative is negative. And on the right, your first derivative is positive. At this value, the first derivative is 0 or undefined. Right? Points that where the first derivative is 0 or undefined will be called critical points. I'll actually define that in a later lecture. But right now, you don't need to know it. But this is how you'd identify a maximum point. So we know that if we have a parabola, for example, maximum and minimums occurs at the vertex. But if I gave you any other random function, there's no formula for the maximum and minimum. How you're going to figure it out is using derivatives. Because the derivative will tell me when I'm increasing or decreasing, I can use that information, piece it together, and figure out when a maximum or a minimum is. So this is what identifies a maximum, that's what identifies a minimum, and this is what identifies increasing or decreasing. The first derivative is what gives us this information, right? So if I need to find a location, a point on a graph, use the original function. If I need to figure out where I'm increasing, decreasing, where I hit a maximum or a minimum, I look at the first derivative. I do not look for information here, up here. I do not look for information here, down here. Know what function you should be looking at to get what information you need, right? So if I give you a function, I say, find where this function is as large as possible, right? This is a function that represents the profit. Find where the maximum profit occurs. You'll be looking at the first derivative to figure that information out. And this is how you do it. You would be looking for a point where the derivative is 0 or undefined, and on the left it's increasing, on the right it's decreasing. That will give you a maximum point. If you're decreasing on the left, increasing on the right, that gives you a minimum point. Any questions? Okay. We're going to copy that down because I will need space. Basically from 2.4, this table is what you need to know. So if you want to reread your notes, read through everything once, but if you're going back to it for study, you're going to just read this table and move on. Efficiency. Right? By the way, we can assume here that all these guys are continuous. The discontinuous case we'll actually deal with later on, and I'll tell you the nuances there. So for one example, this could be a position function, this would be a velocity function. And that will tell you a lot of stuff we're going to apply to. So after you erase that, I'll tell you about the second derivative and what that tells you. not going to want to delete it. We're moving on. Let's talk about the second derivative, what kind of information that gives us, which I kind of hinted to you already, but let's put it in the table. Now the next function is the second derivative. Now what does that tell us? What information do we get from the second derivative? Well, concavity. It tells us when something is concave up, concave down, and of course by extension it tells us where inflection points will occur. So that's the information, right? So if I ever want to find where something is concave up or concave down, or where an inflection point will occur, the second derivative is the function I'm going to look at to get that information, right? How does it tell us that information? Well, concave up means the second derivative is positive. That means you shape like a smiley face, up like a cup. Concave down means the second derivative is negative. That means you shape like a frowning face. Now let's talk about inflection. Inflection point is where you switch concavity. Right, so let's say you have a point x, where on this side your second derivative is negative, and on this side your second derivative is positive. This point, your second derivative is 0 or undefined, but your function is continuous. Then this point is called an inflection point. Right? So over here your negative means you shape like a frown. Over here you're positive, like a cup. So when you do a test and your thing looks like this, it means your graph did something like that. Or possibly something like that. Right? It could be increasing or decreasing, that's not the information. This just tells you, do I shape like a frowny face or a smiley face? Right? And this will be the analysis. And of course the opposite could be true, it could be positive here and negative here. You'll again get an inflection point. So for example, if you ever need to find an inflection point, what you would do is find the second derivative, figure out where it's 0 or undefined, figure out if the signs change on either side. If the signs change, it's an inflection point. If the signs don't change, it's not an inflection point. So yeah, each function gives you a specific kind of information. The original tells you about location, points on your graph. First derivative tells you about increasing, decreasing, maximums, and minimums. Second derivative tells you about concave up, concave down, and inflection points. Do not look at the wrong functions to figure out the wrong things. Make sure you know, when you're looking at a function, what is the information I can get from this function. You'll need to know that for curve sketching. You'll also need to know that for word problems, based on what I'm asking you to find, you'll need to know which derivative should I be looking at. Right? So that's very important information. That's the summary of 2.4, so you need to know that too. Any questions? That's kind of just stuff you should know. So nothing really to figure out. So for example, if I'm giving you some function like that, for example, and you want to graph this, so let's say this function represents something meaningful to you, and you can take my word for it. We'll actually know why this is true later. The derivative is going to be that, right? And your second derivative is going to be that, right? So you're going to have two forms of analysis that you're going to want to do on this guy. So you know that your points come from this picture, from this function here, your derivative comes from this picture. If I wanted to figure out increasing, decreasing, or maximums and minimums, I would set the derivative equals 0, would give me x squared minus 1 equals 0. What's the solutions? X equals plus or minus 1. Now if I tested that on an interval, minus 1, positive 1, what I would do is, in the first derivative, in y prime, plug in numbers in between, right? Like I'm testing an inequality. So I can plug in like a minus 2, a 0, and a 2. And I'm going to plug it into the first derivative. Now if I plug that into the first derivative, plug in x equals minus 2, do I get a positive or a negative number? Right, I would get a positive number. That means increasing. Plug in a 0, positive or negative. I would get a negative number. That means decreasing. Plug in a 2, positive or negative. So it would be a positive, which would mean increasing. Now the function is continuous, it's a polynomial, which means this point gives me what? It's a maximum, right? This point here will be a minimum. So I know what a maximum point and a minimum point occurs on this function, locally anyway. And what if I need to find the coordinates of that maximum or minimum? Plug it back into the original. I can figure out that at minus 1, comma, plug in minus 1 here, I get minus a third plus 1. I get 2/3, right? At minus 1, comma 2/3, I will have a maximum locally. Here, at 1, plug it in here, I get minus 2/3. I know at 1, comma minus 1, 1, comma minus 2/3, I will hit a maximum point. Now I can do a second level of analysis, talk about setting the second derivative equal to 0. These are polynomials, they're never undefined. That means 2x is equal to 0. This means x equal to 0. So now, 0, I'm going to test in the second derivative. So I plug in a number over here, like minus 1. This would give me a negative number. Now, negative in the second derivative means what? Concave down, which means I'm shaped like a frown, right? Over here, I plug in a plus 1 into this, I get a positive number. In this context, it means concave up like a cup. So now what's going to happen is, if I wanted to graph that function, and hence answer a lot of questions about it, I know the function is going to look something like this. You'll find the intercepts later. The intercepts are not what I'm worried about. But I know at this point, I will be at a maximum. That will happen when my x is minus 1. The corresponding y value will be 2/3. Right? So this will be at a point minus 1, comma 2/3. To figure out that point, the lowest point I attain in that region, that will occur when x is 1. And this will be minus 2/3. Right? So here's a random function, and I could figure out the max or min. Right? It's not a parabola. There is no vertex formula. But I don't need a vertex formula. I have calculus. Right? Give me any random function, I can figure out when maximums and minimums occur by examining the derivatives. Right? And I know, for example, like from here, this whole side, notice how my graph is shaped. It's shaped like a frowny face, right? On the whole right side, my graph is shaped like a smiley face, right? So not only I know the highest and lowest points I hit, I know how I should shape while hitting those points. And that gives me a lot of information all on its own as well. Curve sketching we're actually going to do in detail. That's in a later chapter. I think that's on the material for the third test. Right now, just kind of know the derivatives and the meanings that they give you, how you can interpret them, and so on and so forth. So the things you wanted to remember from 2.3 is the formula for the derivative by limits. And from 2.4, what you want to remember is that table that I gave you. Right? That's going to come in handy for later. Any questions? We won't get far, but let's start chapter 3.1. We're going to talk about derivative formulas. I'll probably only get through one in the time we have left, but let's actually do it. Let's do some calculations. as you realized from the first test, doing limits can be cumbersome. We want shortcuts. When do we want them? Now. Right? Turns out there are formulas. There are some functions that behave in a sufficiently predictable way that I can figure out what their derivatives are without even actually doing the difference quotient. So let's look at one example. One formula is called the power rule. So suppose y looks like this, x to the nth power. N is a constant. And let's make it here a non-negative integer. Then, if I asked you to find y prime, what would you do? What's the limit as h approaches 0? Is y of x plus h minus y of x all over h, and we start to plug that in. This gives you x plus h to the nth power minus x to the nth power over h. Now you learned this in algebra, the binomial formula. You don't need to remember it, but that's what we use. What you do is you'd expand this using the binomial formula. You'll get x to the n plus n x to the n minus 1 times h plus n times n minus 1 over 2 x to the n minus 2 times h squared plus blah blah blah. You'll end up with h to the n minus x to the n. What happens is this x to the n will kill that x to the n. H is a common term everywhere else. You'd factor it out. Here you get n x to the n minus 1 plus n times n minus 1 over 2 to the n minus 2 times h plus all the way down to h n minus 1 all over h. H's would cancel. Now you can plug in h goes to 0, and what do we get as the result? If this goes to 0, everyone else has an h and it goes to 0. What are we left over with? This guy right here. So it turns out you can actually predict what the answer will look like whenever you have a function that looks like that form. This gives us the following. The derivative of a function that looks like x to the n is equal to n x to the n minus 1. This is something that we know now. This is called the power rule for derivatives. It's something that you need to memorize. You don't need to know the derivation, you just did that for fun. You need a different proof if n was not an integer, but we need some more sophisticated machinery for that. So I thought it would be cool just to show you what would happen if n was an integer and how things will expand. If n is not an integer, just let me make that note. It works for non-integer n's as well. Right, so remember the form here. What you really need to remember, base is n, x, n is a constant, any constant. Right? If that is the case you're in, that's the derivative. So, for example, if I told you that f of x was the function x, and I asked you what is f prime of x, it will be 1. Why would it be 1? Well, x means x to the 1. You bring that 1 down in front, you get 1 minus 1. You just end up with x to the 0, which is 1. Right? Or if I asked you, what if f of x was x squared, what would be the derivative? Bring that 2 down in front, subtract 1 from the power. It's 2x to the 1. And remember when we did the difference quotient, we did that whole thing and we multiply and expand, that was the answer that we got, right? What about if f of x was x cubed? Who wants to expand x plus h cubed? Nobody, right? You don't have to. The derivative is going to be 3x squared. If you had gone through the whole difference quotient and taken the limit and simplify and expand, that's what you would end up with, right? F of x equals x to the 50. Let's expand x plus h to the 50th power. Not something I wanted to spend my evening doing. The derivative is just going to be 50x to the 49. If you went through the whole difference quotient, took the limit, expanded and simplifying, that's what you would have gotten as a result. Let's make it a little more complicated. Square root of x. We actually did that, right? The answer was 1 over 2 radical x. It turns out that that works here. How does that work? It means a half power. I can rewrite this as that, and that is that form. It's x to a constant power, which means the derivative is going to be what? Take the half down, or these are the power. Right, you subtract 1. A half minus 1 is minus a half, or I could write that as 1 over 2 x to the half. 1 over 2 radical x. Didn't have to rationalize or any of that crap, right? That's your answer, right? Turns out, if your function looks like this, that is your derivative. You do not have to go through a difference quotient, unless you're specifically asked to use a difference quotient, right? Which is why I emphasized last class, how a problem would be phrased makes a difference. If they say, use limits to find derivative, you have to do what I did last class. If I just say, oh, you need to find derivative, do the shortcut. So that will save you a lot of energy. A lot of functions look like this. We'll talk more about formulas next time. So we'll stop there for now. But yeah, know what the derivatives mean, how you can interpret them, know what the first derivative gives you, what the second derivative gives you, know the power rule. We'll have lots more rules to come, and you'll need to know when to use them. If you need to talk to me, we can talk for a bit after class. And I will see you. I don't see you at all next week, right? No. So, week after next.